Spacecraft have reached every planet in our solar system, yet we have barely explored the space directly above and below the Sun. Our planets orbit the Sun on a flat, shared plane. But what lies directly above or below this solar disk? It seems simple. Just point a rocket straight up and go. However, physics makes vertical escape surprisingly difficult.
Escaping vertically is much harder than traveling to other planets. The reason lies in the immense speed we already possess.
The Earth moves around the Sun at roughly 30 kilometers per second. This sideways motion is inherited by every rocket we launch. If we want to reach another planet, this sideways motion does most of the work. We just need to adjust our trajectory slightly. But what if you want to go straight up, perpendicular to everything else? That sideways motion becomes your enemy.
To go straight up, you first have to cancel out the 30 kilometers per second you already have. Then add new velocity to climb.
Mission planners call this change in velocity delta V. The energy required to leave the orbital plane is staggering.
Going to Mars from Earth's orbit needs about 4 kilometers per second of delta V. Vertical escape needs nearly 10 times as much.
Earth's orbital motion gives us free speed in one direction, effectively trapping us in the plane of the ecliptic. It is one of the most counterintuitive facts in astrodynamics. Reaching Pluto is easier than reaching a point just above the Sun's North Pole.
Because the vertical exit is so expensive, almost no spacecraft has ever made the trip. Most solar activity remains unexplored.
The polar regions of the Sun are where the most violent and important solar activity actually happens.
The magnetic field of the Sun reverses itself every 11 years, through processes that begin at the poles.
The entire space weather environment of our solar system is shaped by what happens above and below the equator of our star.
There have only been 2 missions that ever managed a real polar view of the Sun. The first was Ulysses, launched in 1990.
To get out of the ecliptic plane, Ulysses had to take a wild detour, using Jupiter's gravity as a slingshot.
This maneuver bent its trajectory nearly 80 degrees out of the planetary plane, allowing it to fall back toward the Sun.
Ulysses gave us our first measurements of the fast solar winds, but it had no cameras capable of imaging the poles.
The second mission is happening right now. Solar Orbiter, a European Space Agency probe, has been gradually tilting its orbit.
In 2025, Solar Orbiter sent back the first direct images of the Sun's south pole ever taken in human history.
The pictures show a chaotic, magnetically tangled region, nothing like the smoother solar surface we see from Earth. Think about that. Until recently, no human or robot had ever seen what the top or bottom of our Sun looks like. There is a second reason vertical escape matters. We do not actually know what our own solar system looks like from outside. Around the Sun is a vast bubble called the heliosphere. It is the region of space where the solar wind dominates. Inside this bubble live the planets, the comets, and every human spacecraft we have ever launched. For decades, we assumed the heliosphere was shaped like a comet, a rounded front and a long, trailing tail. The new prediction looks closer to a deflated croissant, a curved central bulge with two short jets curling away from it.
The Voyager spacecraft crossed the heliopause sideways, useful but not enough. We have never seen our bubble from outside.
There is a NASA mission called IMAP, the Interstellar Mapping and Acceleration Probe, designed to refine our understanding from the inside. It is called the Solar Oberth Maneuver. The idea works backwards from how rockets normally fly. You drop your spacecraft toward the Sun, letting it fall inward, accelerating under solar gravity until it is moving at hundreds of kilometers per second.
Then, at exactly that moment, you fire your engines. A rocket burn is dramatically more efficient when performed at high velocity.
The fuel you carried up from Earth turns into far more kinetic energy than it would have anywhere else.
The Voyager spacecraft crossed the heliopause sideways, useful but not enough. We have never seen our bubble from outside.
Sails can take years to spiral up to a polar orbit, but they need no propellant. Combine the two, a spacecraft that uses a solar sail to spiral closer to the Sun, then performs an Oberth maneuver at perihelion. This is the kind of mission architecture that scientists now think could finally give us a clean view of what lies above our star. First, the view changes physically. The ecliptic plane is dirty. Earth swims through a thin haze of dust left over from billions of years of collisions. On a very dark night, a faint pyramid of light, called the zodiacal light, reaches up from the horizon. A spacecraft that climbs above the ecliptic would rise out of this dust within months. The view there is dramatically cleaner. Second, the solar environment changes. Above the poles, the slow solar wind gives way to something steadier.
Above the polar coronal holes, there is a stream of fast solar wind, particles flowing outward in a thinner, smoother current.
And third, the bigger picture. From a vantage well above the ecliptic, the solar system itself would be visible as the disk it actually is. You would see the planets in their flat ring around the Sun, with the dust hugging the plane and the heliosphere wrapped around all of it.
We would be able to look down at our own neighborhood for the first time, the same way we look down at Earth from orbit.
We have never seen this view. Not a single human or robot has ever sent back the photograph. If you had to design the first mission to climb directly above the Sun, would you bet on a solar sail or an Oberth dive? Tell us in the comments. And if you want to know what is actually waiting up there, watch what exists above and below our solar system next.